Alright. So, last class we talked about rotor in climb condition, and we were sort of discussing that what happens when instead of climb my rotor starts to descend. So, rotor is generating thrust upwards, but it is descending, which means my V c is in this direction. So, it starts coming from down. So, we argued that because of this my flow somewhere it could be going down, somewhere it could be up. So, the resultant airflow as a combination of the induced velocity, which will be V I, and this V c. So, the combination of V I and V c would actually create a scenario that some places your flow is upwards, some places flow is downwards. So, there is a lot of circulation happening, and the primary inherent assumption which we made at the beginning of the momentum theory discussion was that my flow is all nice one dimensional, right. We said everything is coming down in a nice streamlined manner, which would no longer hold true when the rotor is in descent. So, the catch is that for normal descents, when you are descending at lower speeds, you cannot apply momentum theory. But yes, there is a condition where you can guarantee that my flow is always upwards. So, let us see if my V c is more than twice of V h. So, my V h, we know that if I am climbing or descending, my V I would be less than V h, right. So, if I put a barrier that twice of V h is what I mean. So, if I look at my control volume again, so if my rotor is doing this V I, far down it is twice of V I, right. So, now if I say that my V c here is more than twice of V h, which means everywhere my resultant flow would be upwards, right, because what happens here, it will be V c minus twice of V I, here it will be V c minus V I, right, and all the flow is now upwards. So, maybe I can change color to highlight this better. So, everywhere I can now assure that my flow is upwards. So, this can only be assured when my descent rate is more than twice of hover induced velocity. And we saw for the example problem we solved for our UAV, which is 6 meters per second, right. So, twice of VH is 12 meters per second. Can you imagine a UAV descending at 12 meters per second, right. 12 meters per second is like 40 kilometers per hour, give or take, right. So, you will not find even airplane descending at that fast rate, when it is coming to touchdown or something like that. So, that is a fairly high rate and it is only theoretical for us, it has no practical significance, but in that condition I can certainly apply momentum theory, but it is of no practical significance because this condition is beyond a condition called windmill brake state. And for overall we talk about any rotor having 4 different operating states. So, we can say operating state of rotor or working state of rotor in axial flight. So, we say 4 working states of rotor in axial flight. What is axial flight again? Yeah, when the airflow is parallel to the axis of the rotor or your propeller. So, if I take the fixed wing, go back to my fixed wing airplane and the airplane is in forward flight, is the flow across the propeller axial? Yes, no? Some of you are saying no, some of you are saying yes. Why it is yes, why it is no?
It's flying like this.
Yes, it is flying like this.
Actually, the flow is
yes. So, the flow is still parallel to the axis, right. My propeller is spinning like this in the vertical plane, right, and if this is my axis, it is going in that same direction, parallel direction. So, it is still axial flow. So, that is your axial flight. But when my rotor is or my quad rotor, when it is doing forward flight, Is that also axial flight? Okay, what is the name for that flight?
No. Transverse?
No, the rotor is in edgewise flight as opposed to axial, that is called edgewise, which means my rotor is like this and it is dragged along the edge. So, in forward flight it will slant like this slightly, because you have to get a thrust component in the propulsion direction, right. So, it is slightly tilted 10 degrees, 15 degrees, 6 degrees, 4 degrees, whatever. So, my rotor normally in hover is like this, it will tilt like this and then go forward. So, this kind of flight is called edgewise flight as opposed to the axial flight. So far we have only talked about axial flight, we talked about hover, we talked about climb, and we briefly mentioned descent, and now we will analyze descent in terms of these different states of rotor, and I will give you some empirical formulas to estimate induced velocity in descent condition, which could be useful for flight dynamic modeling and several other things. Okay. So what are the 4 working states? First one, which we have looked extensively, is the normal working state. Which is hover and climb. Okay. So, both these conditions are fairly similar. So, everywhere I have flow in nice uniform same direction. So, flow is downwards everywhere in the control volume. Okay. So, this working state is applicable for my hover as well as for climbing flight for a hovering rotor, or if I look at a propeller in forward flight, that is also same kind of thing. Remember in the video I showed you one cargo airplane taking off and helical vortices shed behind that, right, which is very similar to the rotor hover video, where you could see the tip vortices actually going around the person who was flying it, right. Okay, so same thing. So, they are both very similar, slightly different, but they are both axial flights and they have similar kind of flow as shown here. Now, second flow condition happens when you go in descent. So, other 3 operating states are all corresponding to descent. They are all also axial flights, but in descending condition, when you are trying to come down and there are 2 opposing air velocities, one is your induced velocity from the rotor, another is your downward movement. So, the relative flow because of that. Yeah, so, airflow will hit rotor from down to up, while the induced velocity is coming from top to down. Okay. So, there are 2 opposing velocities and these velocities will combine and do some funny things, and these funny things are not so funny in the sense they are scary. Okay. So, one is the dreaded VRS. Also called VRS. So, this happens for low rate of descent. So, how do I define low rate of descent? Well, when my Vc is of the order of quarter of Vh or more, this is the limiting condition. If it is more than quarter of Vh, so for my Subl 20 we said, I mean we obtained it 6 meter per second is my induced velocity, ideal induced velocity. So, if I descend at speed is higher than 1.5 meter per second in vertical descent, then I have a possibility of entering this condition called vortex ring state. So, I will give you first theoretical explanation of this, and there are also some videos and actual practical scenario what this vortex ring state could lead to, what can it actually cause. So, in this case what happens is that these vortex filaments which we are seeing coming down nicely, they will all try to get pushed up towards the rotor, okay, because there is some induced velocity coming and there is downward velocity coming, and they are going. So, the downward speed is going to push it up, and it will happen that this filament will rise up and sort of start bundling around the rotor plane. So, we can take a maybe okay. So, I will go to the next slide, and yeah. So, let me draw a diagram for this, how it looks like. So, let us say this is my rotor. Okay, so it will have this kind of strange looking flow field. So, this is flow recirculating, and this is somewhat violent in the sense that this is very aperiodic. Slipstream goes beyond rotor disc, okay. So, what happens that as Vc goes beyond 0.25 and reaches almost value equal to Vh. So, as you keep going beyond, so it is not like I mean the moment you reach 0.25 it will dharak happen, okay. It will not happen like magic, but then you are slowly pushing the vortices to bundle upwards. So, what happens that? So, as this goes, rather as this happens, the tip vortex filaments convect closer to the plane of the rotor, and also move radially out. Okay, or radially outward from the rotor, and that is what you are seeing in the diagram. Okay. And this entire thing is very unsteady and aperiodic, unsteady and aperiodic, and so what happens is that I mean the flow, my vortex filament, my shed helical vortices, they are getting pushed upwards and they will try to sort of bundle up together. So, it is like you may have played with a toy which is this helical kind of thing, right, which stretches. Okay. So, it is like I mean if you compress a helical spring, it will all come stacked very with high density in a closed form thing, and it will also bulge up So, it will like a barrel, it will become bulged up in that direction, and so this we say that, I mean, the accumulation of tip vortices. So, this bundling up of tip vortices in the rotor plane resembles, or rather begins to resemble, concentric set of vortex ring or ring of vortices. Okay, and hence the name vortex ring state. It sort of starts forming a ring of vortex around the rotor, and it is not in contact with the rotor, it is slightly away from the rotor. So, you will have a ring of vortex around it, but then how does it affect me? Okay. So, from the point of view of piloting, it is very dangerous, because this vortex ring being very aperiodic can cause sudden drop of lift. So, you are flying your quad rotor, you are flying your multicopter, helicopter, whatever, okay, and you are descending too fast, and suddenly your thrust will be lost. It is not very hard to actually create this. So, at one point I had bought a $100 toy quad rotor, which actually had brushed motors. So, it did not have very precise RPM control, and the autopilot on that was also very rudimentary. It was just basic your attitude controller based on rate feedback mostly, and it did not have any means of controlling height, vertical speed, etc. So, if you pilot it and you want to, taking off is fine, climbing up is fine, the moment you try to land, the throttle was very sensitive. So, if you are in hover, and the moment you reduce it slightly, it will start sinking very quickly, and you could see, I mean, it will enter vortex ring state. But what happens when it enters? So, let me show you a video. So, here is some guy who is flying this DJI Phantom 2. So, till Phantom 2 and all, I mean, DJI folks were not aware of this phenomena called vortex ring state. So, their autopilot did not actually cater to all these problems. So, you could descend at any rate you want, you could descend very fast also. So, there is some guy who is somewhere in Europe, he is flying, you can see other quad rotors are also being flown. So, people are flying it for fun. So, he has bought some new carbon fiber propeller to replace the normal plastic propellers on DJI, and he wanted to test it out. So, he is flying, and then, so you are seeing this nice, it is a gimbal camera, which DJI has been doing very well actually. So, their camera systems have been fantastic from day one. Actually, earlier they Phantom 1 they used GoPro with a basic gimbal. By Phantom 2 they actually had done integration of the camera, everything, and they kicked out GoPro, and after that GoPro actually had a serious downfall in terms of its share prices and everything, and they thought, okay, fine, DJI is no longer buying our camera, so we will make our own drone. I do not know if you are aware of the drone made by you are aware of GoPro, right? Yeah, the action camera, okay, which is waterproof and nice and all that. So, they launched a quadcopter, and at that point of time my classmate was also working in GoPro. So he is my batchmate from Kharagpur, I mean from physics department, somehow, I mean, because he was into electronics and other things. So, he got involved, he was working in GoPro. So, he told me that, I mean, so they decided, okay, we will make this quadcopter, and they thought, the quadcopter, what is the big deal? I mean, we are making this so complicated fantastic camera, we will make a quadcopter. So, fortunately, unfortunately, they called it Karma. And fate has to be it turned out to be bad karma. So, whatever karma they had sold, they had to recall the entire thing, and they said, no, we will only make cameras, we will not do quadcopters anymore, because it started falling from sky. They basically tried to push it too quickly. They have not done enough testing, they have not done enough system engineering and checks, balances and so on, and so they had to recall the whole thing, okay. And yeah, turned out to be bad karma. Yeah. So, right. So, now you see this very nice stabilized video camera is slightly foggy, but you see what is happening now, okay. You see the propeller. So, this gimbal is stabilized. So, camera is not moving, something else is moving. no damage except my pride. That is very brave of the guy, but he is also not aware. I mean, his quadcopter has entered vortex ring state. So, the whole thing starts shaking violently like this. And now you can imagine, I mean, as a pilot, what would you do if you feel that, I mean, you are trying to descend and suddenly it is sinking too fast? What is your inherent tendency? What would you want to do or try to do? Increase throttle, right? Okay. You will say, okay, more throttle. Bad idea. It would make things worse for you. So, if you ever see that, I mean, your UAV is going to enter vortex ring state, you would not want to increase more power. Okay. And helicopter pilots, they experience this quite often. A lot of times they are operating in very constrained environments, or they have to land sometimes to avoid something, or to because of some disturbance they may have to sink too quickly, and if they end up entering vortex ring state. So, what happens that the immediate tendency is that I am dropping too fast, so let me pull up. So, I will pull collective more on a helicopter, which means basically putting in more power. So, here also you are giving more throttle, means you are giving in more power. So, it actually makes things worse, and that is why people call this settling with power or power settling phenomena. So, from a pilot's perspective, who is not very familiar with aerodynamics, they call this as settling with power. Means, I mean, we have to accept that we cannot give more power. So, we are doing some settlement with power. So, I do not know why they call it, but it is called power settling or settling with power phenomena, and they experience through loss of thrust. Let me show you another video.
So the way to recover out of this is to
Coming to
reduce
that.
the thrust.
Coming to that, yeah, something more serious. So, you recognize this craft? Ospreys, right? So, two of these Ospreys were coming back from some sortie, and they were supposed to land at Marana Air Force Base in southern Arizona. This video is from, it is a similar video from almost 25 years back. So, I have taken this video from YouTube. Okay. So, not my original thing. So, I must acknowledge whoever made this, the company called Trial Exhibits. This was part of some crash investigation report basically. So, both these are coming and trying to land. So, this guy is descending, the guy at the back, he also starts descending, but it starts descending too fast, and this is what happens, and that dreaded what? Vortex ring state. So, pilots also call this as a helicopter sinking in its own wake. So, they use this another funny term, you are sinking in your own wake. In just its own downwash, it loses lift. See, the ring of vortex forms here. It is called vortex ring state. So, you see now the wake visualization. The downwash will look like this. When you start descending too fast, this wake would get pushed upwards. Near vertical descent at over 2000 feet per minute. Okay. Let us watch this completely, then we will take your question. Yeah. You see, right rotor enters a vortex ring state and loses lift. Okay. So, it could have happened to any of the rotors, and yeah. What is the question?
It happens when V climb is lesser than V hover, 0.25 times, lesser than 0.25 times.
No, more than.
More than 0.
More than, yeah. So, up to 0.25 it is fine, it is fairly safe. If you go more than that, then it becomes tricky.
So why is it 0.25?
it's this approximate number, it's not exactly that it will magically happen that, but up to that I mean we know it's safe. Okay. So, here we can see a nice CFD simulation also taken from internet. I cannot acknowledge the exact author, but yeah, somebody did some basic simulation and you can see. So, here the rotor is upside down, okay. So, wake is going upwards. So, you see this, you saw the ring in the filament form also you can see that barreling, right. So, the wake is no longer attached or my free stream velocity is no longer constrained to the boundary, it actually you see it bulges out so much. It is very turbulent. In this case you can see it more clearly, you see, and like I mentioned, it is very violent, right. You see it's fluctuating so fast, right. It is oscillating ring of vortex, and this may cause sudden drop of thrust. So, this is also a video taken from YouTube, done by some helicopter training company in Switzerland, and so they call this as a Weichert technique of recovery from VRS, and it's very basic thing, it's simple. The moment you feel that I mean you are losing lift or losing rather thrust, you have to basically get out of axial descent, either fly sidewards or forward, backward, whichever direction. So, get into forward flight immediately and this will go away. So, for a quadcopter, so the same thing, I mean I was descending and it started descending too fast and it was close to where my car was parked. So, I got really panicky, but I immediately gave a, because I was aware of this. So, I gave a pitch. So, it started going sideways and it came out of vortex ring state immediately. So, here you see same thing happening, then they will turn on the flow or flow visualization and then you will be able to see the vortex getting created very nicely. Yeah, now you see with the wake turned on. So, you can see the ring of vortex 2D of that and they will try to move sidewards. You see it starts moving sidewards and that breaks down the vortex ring. Yeah. So, when you are descending vertically you will get into vortex ring.
But the helicopter doesn't seem to have any violent effects.
Sorry, what?
So this helicopter doesn't seem to have any violent effects on it yet.
No, it is sinking and it is sinking in a very deep valley and it slowed down video. Yeah. And they are not going to let it happen for several seconds. Yeah. They will not make a video just to become popular, right. So, they want to live to train other people also for this. So, the moment it enters for a brief while, they will immediately give a cyclic and come out of it. Yeah. So, that is the basic trick. I mean you want to get out of axial descent and then you are safe from the vortex ring state. Okay. So, now we will just complete the discussion about this. Is dangerous from piloting or autopiloting, means when you are trying to program your autopilot for certain things. So, even I mean now most of the UAVs are doing complete autonomous flight where you program it will do auto takeoff, do the mission, come back and do auto vertical landing. So, while doing auto vertical landing, your autopilot must constrain your speed. So, that is where I mean you have to be careful in specifying what vertical rate of descent you are going to allow. So, under no circumstance I mean the quadcopter can come down or your UAV can come down at a faster rate than what you specify, and that has to be quarter of less than quarter of your hover induced velocity. Okay. Note that the VH is an ideal term. Okay. So, in real world I mean you will multiply it with your induced power factor, right, that kappa, to get a more realistic estimate of your induced velocity. So, 1.15 into 6 will be 6.9, yeah, 6.9 divided by 4 is whatever it is 1.7, 1.6 whatever. So, that will become your limiting value for your descent. Okay. Or just to be safe, I will not take this thing and I will simply use my ideal induced velocity, take a quarter of that and put that. I know it is going to be less than my quarter of actual induced velocity. So, I am safe again. Okay. Point of view, because as it can cause loss of thrust and intuitive response of putting in more power to arrest my descent makes it worse. Okay. So, pilots, helicopter pilots call this settling with power. Okay. Or power settling. This can, we saw it happening for Osprey, okay. It can happen for any VTOL for that matter. And yeah, I mean at one point I was doing a project for this one company, okay, who had to deliver their loitering ammunition, VTOL loitering ammunition to Air Force, and their drones were crashing. So, apart from other problem, in one particular flight, I mean they were just flying it as a quadcopter, just checking out climb, descent, I mean like just take off, landing, etc. The video was exactly similar to, so they sent me a video and the video is exactly like the Osprey video. The pilot was trying to descend and it just flips over and crashes. So, I told their autopilot developer that, I mean, did you look at what are the rate of descent, because this video is very simple and obvious, it is a VRS problem, your one rotor entered VRS. So, that person told me, yeah, we are aware of VRS, but who worries about VRS these days? We are like, what? So, you stop worrying about VRS, that means it goes away, it is no longer in fashion to look at VRS, vortex ring state. So, anyway, so that was a surprising answer for me, but nevertheless, I mean they got the idea. Okay. So, but yeah, other problem was a different problem which for which their drones were crashing, which we solved eventually. But this VRS can also be troublesome for conventional helicopter tail rotors. How? Okay. So, this is my conventional helicopter.
At a age,
Yeah.
aging velocity will be there on tail rotor.
What velocity will be there on tail rotor?
Aging velocity, age velocity on that bow.
You are saying there could be a side wind.
Yeah.
So then gust can
Yeah. So what happens that, I mean, if my helicopter is in hover, right, and there is side wind coming from say right to left or left to right. So, in one case your rotor will experience climb conditions, okay, depending on which way the rotor is giving thrust, tail rotor. Okay. So, this is also giving some thrust. So, it could be maybe giving into the board or rather into the plane of this screen. So, if my wind is coming from that side, that will be climb, right, okay. But if the wind comes from the other side, that is your tail rotor will go in descent condition. So, which means that my helicopters, even full scale helicopters, any kind of helicopter is always vulnerable to wind coming from one direction. So, they do not like crosswind much, especially from one side, because then your tail rotor can enter VRS. If tail rotor enters VRS, what will happen? Suddenly the rotor will, your helicopter will yaw, okay. Or it can even be created by making a helicopter yaw very fast in that direction, okay. So, if I make the helicopter yaw about this direction very fast at high yaw rate, then this point will again move in this direction, which will create the rotor in descent condition, okay. So, tail rotor VRS can reduce or cause loss of tail rotor effectiveness. So, your capacity to counter the torque would come down, or it can even vanish altogether if it truly goes into VRS. Okay, so, suddenly your helicopter would yaw, but the good part is that the moment it yaws, you will be away from the side wind direction, which should hopefully solve the problem, but still it could be unsettling for the pilot, because if he is trying to maintain its heading in a certain direction because he is doing some task and suddenly the helicopter yaws. So, that is undesirable and that can create challenges, accidents and all kinds of things.
So, the tail rotor is generally moving opposite direction of the, or is designed to give thrust opposite to the direction in which the top rotor is moving, right?
Yes.
So, then also it can give the descent.
No, but it has nothing to do with my main rotor. No? See, whichever way, your rotor is, your tail rotor is in vertical plane, right. So, my wind can come from this side, it can come from this side.
Then it's also giving lift because of this.
No, not lift. See, tail rotor is generating some thrust, say let us say in this direction, okay. So, my wind, if it is coming from that side, would cause my tail rotor to experience as if it is in climb, right. If the wind comes from behind, it will create as if it is in descent, okay. So, what happens that, when we look at helicopters, right. So, we often talk about drawing the wind profile map. So, I can say that the kind of wind speeds my helicopter can handle from different directions. Okay. So, here some things could be there, but when it comes from the other side it will be probably smaller. So, I can take wind from many directions, but when my tail rotor enters VRS, in that direction when it goes in descent, I can only take very small amount of wind. So, it is vulnerable to side wind from a certain direction.
From a certain angle, can it reduce the VRS?
It will also reduce the effectiveness of your tail rotor to counter torque. Okay. So, this is one known challenge in any helicopter of conventional type. So, pilot would not want to, so if he is aware of the wind, the direction of the wind is facing, he will probably want to hover by facing it, okay, not being side of it. Okay. And many helicopter crashes happens because of some of these things actually, because suddenly it is hit with some side wind and the tail rotor will be lost and he will suddenly yaw. And if he is hovering in a constrained environment, he can hit something or all kinds of things can happen. Okay. So, this is our vortex ring state. Then we go to the third state. okay, which is called the turbulent wake state, which is similar to this vortex ring state, but it happens beyond that. And even though the name is turbulent wake state, it is less dangerous because by now my rate of descent has already gone higher than Vh. Okay. So, I am descending at much faster speed, and therefore, now most of the flow is going upwards. So, if I draw the diagram, so vortex ring would have probably become narrower, okay. So, once again this is my tip path plane or rotor plane. So, if my descent velocity increases, if my Vc is of the order of 1.5 times Vh, okay. So, what happens is that the wake above the rotor disc is more turbulent and aperiodic. Slipstream boundary becomes somewhat well defined, and the key takeaway is that the flow field is similar to that associated with a bluff body, okay, which means so if you take a cubical object and put it in a flow, so the kind of flow it will experience around that, it will be very separated flow with lot of turbulence and wake perturbation. So, this rotor will have similar kind of flow field resembling like a bluff body, and so this is less challenging compared to VRS. So, idea is that if you have gone beyond VRS, you will survive if you have not gone there. So, if you are in turbulent wake state, you can still have a flight, and interestingly the auto rotation happens. Okay. So, the auto rotation where there is 0 power condition, and rotor gets powered on its own, and it keeps coming down like it is as if it is gliding, and I showed you a video of our rotary wing UAV doing autonomous auto rotation, right, okay, where it was coming down on its own. So, that particular situation happens in this turbulent wake state. And finally, the fourth state operating state is called windmill brake state. This we say my descent velocity is now more than twice of Vh, which I told you in the beginning. So, when my rate of descent is faster than twice. So, for my subtle 20 this would be 2 into 6 which is like 12 meter per second. If I start descending more than 12 meter per second, my subtle 20 will start generating power, it will become a wind turbine. Okay. So, that is what happens in this. Rotor extracts energy from the flow, tip vortex is back to more usual helical structure, but in the inverted direction. Okay. So, rotor is like this, generate thrust, oops. So, see the flow will all be going upwards. So, rotor extracts energy, and this is quite understandable, because before this, during the turbulent wake state we cross over the point of 0 power. Okay, so, before that power is positive, when you reach autorotation power is 0, which means rotor spins on its own, it is neither taking power from the motor nor generating power. Okay. So, it is at 0 power condition, and beyond that if I go further far down at higher descent rates, now my rotor will start generating energy. So, it starts acting like a wind turbine. So, rotor extracts energy from flow, and tip vortices is back to usual helical shape. Okay. So, we will not derive for the windmill brake state, because you will not never ever fly a UAV in windmill brake state with 12 meter per second descent speed. So, for us, I mean, the two things of major concern are of course the normal operating state, climbing state, and the vortexing state. Vortexing state purely to avoid point where you do not want to go ever.
1.5 and 2.5.
No, what are you saying?
2.5 because
What
from
2.5?
2.5 VH it will go into 0.25.
0.25, yeah. 2.5, yeah, 0.25, less than 0.25, yeah.
So it has to be.
So, between VH and 0 descent rate to up to 0.25 descent rate. Okay. So, quarter of your that speed. So, now we, like I said, I mean we cannot actually model the normal descent that we are talking about. We can only model this windmill brake state, which is of no use to us. So, we will not worry about that. But yes, people did try to calculate your induced velocity, because we may still require this induced velocity for some cases. Okay. I am trying to simulate my UAV coming and landing, and I have a flight dynamics model. So, I need to know what is the induced velocity, because that is only I can get my thrust estimated, my power estimated, everything else estimated with a higher degree of accuracy. So, there are more sophisticated models for modeling wake, such as dynamic inflow models and dynamic wake models or free wake models. So, there are many sophisticated complicated aerodynamic models which allow you to model the induced velocity in a more accurate manner, but we do not have time in this course to look at those things, but we can always look at the simplified thing, which is how do we estimate Vi for Vc by Vh minus 2 to 0. Okay. So, when you are descending at speeds less than minus 2. Okay. So, here there is no simple theory. So, I can only get induced velocity through experimental evidence. I will try to estimate this. Also, the momentum theory tells me that my induced velocity is uniform everywhere on the disk, but in these kind of conditions it is not uniform. So, what we are going to do is that we are going to sort of indirectly get a averaged value of induced velocity. Not just it is not uniform, it is also very turbulent. Remember the video where we saw the filaments jumping all over the place? I mean, how would you define a uniform value for that? It is fluctuating, some part is going up, some part is going down, but nevertheless, I mean, I can define some approximate averaged value which can be used for some simple calculations. That is the idea. So, flow is unsteady and turbulent. So, we can find out average velocity can be obtained indirectly through thrust and power measurements. How? So, I can take a so, I take a rotor, put it in a wind tunnel, so that the rotor is in descent condition, and I can keep changing my tunnel speed. So, I can control my Vc, right, and rotor thrust would be in this direction, right. So, I can put this rotor on a balance, load balance, load cell, force torque transducer, whatever you want to call it. I put it on some sensor which will be measuring my thrust and my torque, and I can also measure omega. How do you measure omega? Okay, tachometer. What is tachometer? Okay, optical tachometer. What is optical tachometer?
This is a piece of either
It's
a
basically
reflective
send-
tape or something. On
So
the
basically send pulse of laser and it reflect and we count it on each rotation. So it's give RPM basically. From there we can calculate.
Yeah, I mean, RPM omega is same thing. Whatever unit you call it, okay, it is same thing, right? Okay. So fine. So you can use some kind of tachometer. We normally use a sensor called Hall's effect sensor. Okay, are you aware of Hall's effect sensor? Yeah, so it detects magnetic field. So we can put two magnets in the rotating frame, your rare earth magnets, and put a sensor in the fixed frame very close to it. So it will detect the magnetic pulse, and again you count the pulse using a small code on a microcontroller like Arduino or something, and that also will give you fairly accurate estimate of your RPM. Right. So, other is, I mean, of course, your rotor will have some vibrations, always some imbalance is there. So, if your load cell is very sensitive, the data, if you do FFT of the data, it will give you that frequency automatically, the rotational frequency. So, indirectly also from the data I can extract my RPM without requiring any other measurement device also. But for that your load cell has to be very sensitive, okay, and should be able to capture data at fairly high sampling rates. So, I have thrust and my torque. So, my torque into omega becomes measured power. I can measure it and this as per my momentum theory should be T into Vc plus Vi, right. But this is only the ideal power, I am measuring the power, so it is total power. So, therefore, I must also add profile power, and it is not really ideal power because my T is actually measured thrust. Okay. So, my thrust is real, my power is real, Vc is also real, only thing that is not real is P naught, I cannot measure P naught directly. Okay. So, what I will do, I will use my normal formula from blade element theory, sigma C D naught by 8 etcetera, and get my P naught from there. So, you see now, so this is profile power in case you have forgotten, and this Vi is my averaged induced velocity. Right. So, we can also say my hover power from momentum theory is T into Vh, right. This is normal formula which we have used so many times. So, if I divide these two equations, I can write this as Vc plus Vi bar by Vh equals to P measured minus my profile power divided by hover power. Okay. Well, you can, this is momentum theory, so I can even write this like this, P measured minus P naught into 2 rho a W to the power 3 by 2. So, now with this expression and Vc by Vh I already know it is measured. So, I can get Vi by Vh indirectly through experimental data, and of course, for P naught I can write sigma C D naught by 8 into rho a into omega r whole cubed. So, that is known to me. So, people have done this kind of experiments quite a few times, and they have obtained data, and that data they actually did some curve fitting. And so, there are two set of formulas available. This is taken from Professor Leishman's book. So, there one is actually a straight line fit. So, using this measured average inflow, one can do a curve fitting over the measured experimental data, and they have already specified two set of formulas. Okay. So, which we will see next. So, you understood the idea, right, okay, what we are doing here, and be aware that this Vi bar, we have put a bar on top. Why? Because Vi is going to be highly non-uniform across the blade. We are simply trying to get an averaged value of that over the whole thing to give you some sense. So, there are two sets of formula, one is a straight line fit, where we say Vi by Vh can be given as, one formula is kappa minus 3 by 4 Vc over Vh, another is kappa into 7 plus 3 into Vc over Vh. The first formula is valid for minus 8 times kappa by 4 kappa plus 1 Vc by Vh. So, this is from 0 to this number, and the lower formula is for minus 2 Vc by Vh minus 8 kappa by 4 kappa plus 1. Okay. So, what is this kappa? What is the name for this? You have already seen this, right? Where was this?
Induced power kappa.
Yeah. We used in the figure of merit definition. Induced power factor. So, which nominally we take as 1.15. Okay. So, if you put that here, you will see up to what range the first formula is valid, what range second formula is valid. And then there is a continuous quartic fit, which means it is a fourth order polynomial. So, we directly give V I by V h equals to kappa plus k 1 V c by V h plus k 2 V c by V h plus k 3 V c by V h squared, actually k 2 square k 3 V c by V h cubed plus k 4 B c by V h to the power 4. Kappa is same, but k 1 is equal to minus 1.125, k 2 equals to minus 1.372, k 3 equals to minus 1.718, k 4 equal to minus 0.655. Quartic, Q U A R T I C. You have quadratic, you have third order, this is your fourth order. So, quartic is fourth order polynomial. Okay. And this is valid for the full range for minus 2 V c by V h 0. Okay. And if you draw this, so if I have V I by V h versus V c by V h, you remember the formula we have gotten, it was like this for the positive rate of climb when you are climbing. When you descend, we do not get any solution till, so this say this is 1, 2, I can put minus 1, sorry, minus 2. So, this minus 2 thing will go up to same value. So, from here it will again descend like this. So, this is my windmill break state.
These two are asymptotes, sir.
Yeah, I mean they are asymptotically going to 0. As you climb at higher and higher speeds, the induced velocity will keep on decreasing further. Okay. And this is the area in between which was not known to us, okay, between minus 2 to 0, and that is where we got some kind of this curve fit. Okay. So, I have just drawn it approximately, but this is the area where we are defining the induced velocity now using these two formulas. So, you can use either of them. Okay. So, either straight line fit or this fourth order polynomial fit to get your induced velocity estimate. So, this is your normal state, and this is your windmill brake state. And in between I have turbulent wake state and vortex ring state. Okay. So, this is climb and this side we have descent. Okay. So, this is just to give you an idea that how my induced velocity is changing. See, under every condition when there is clear increase in your mass flow rate m dot because of more flow entering either through climb or descent, your induced velocity will always decrease except between the 0 and -2, because this is an area where there is no clear increase in mass flow. Some air is being pushed down, some air is trying to push it up. So, there is a big hodgepodge, it is a lot of mixing of flow, very turbulent kind of state, not very coherent flow. So, in that scenario we end up getting average inflow becoming more than your hover inflow, and that is when I mean you see also some funny things happening, like you get a condition of 0 power, right, which is your auto rotation, or you get 0 thrust condition which is your vortex ring state, okay, when suddenly your thrust goes away. So, this area is very chaotic area, and we have to operate our UAVs carefully in these areas, which means when you are doing axial descent. But then this poses a lot of restriction also, right. I mean my subhull cannot descend more than 1.5 meter per second. So, if I am climbing good height for some operation and I have to come down, it will take me forever. See, at climbing I can do it maybe 2 meter per second if I have enough power available, okay. I am not carrying a lot of weight, I may climb at 2.5 meter per second. I will burn power, but I can climb if I need it to. But if I have to descend, what do? I cannot descend more than 1.5 meter per second. So, what is the solution? Because in crash, more than pride, there are a lot of things which break. Today morning I got a news that I mean the UAV we have delivered to people on eastern side, somebody just switch it off in the middle. So, we are seeing what happens. So, gravity takes over. Switch off a UAV, gravity takes over, of course. So, please repair now. You switch off a UAV in middle of the flight, I mean what will happen? Okay. So, I mean we trust that I mean people who are operating, they will not try such stunts. So, yeah, so one has to be very, very careful. So, question is what is the solution if I want to descend faster?
So we move away from the axial flight. And
Correct.
descent.
Okay. So, we will not try to descend axially. Okay. There is no restriction in descending when I am in forward flight. Okay. So, then I mean what happens? Wake goes behind away from the rotor very quickly. So, it has no time to create any nuisance. It will not do bundling up, it will not do this vortex ring state creation and so on. And the good part is that I mean I will end up actually operating at very low power condition, because of my forward speed I am already at low power condition and I am descending now. So, I am using gravity some more. So, my induced velocity requirement comes down even more. So, my induced power will drop quite a bit, which is really good thing. I mean I can descend like this very fast, but so in a slant range. Okay. So, I am keep moving forward and descending and save energy also. So, I mean consume 20, 25, 30% less power descending at a faster rate. Okay. So, that is the trick. So, slant descent is better than axial descent, except when you have geometric constraints. I mean there is a hill in front of me. So, I have to cross the hill, then only I can start descending. I cannot descend and go into the hill, right. So, if my terrain permits, I will go on a slant descent. Okay. So, this actually emphasizes the importance of proper mission planning. Okay. So, if you do your mission planning with the awareness of correct things, you can save energy and you can maximize your performance, which most people are not aware of. Yeah. Okay, fine. So, we will stop here at this point. Now, we will go to this forward flight, okay. And after that we will also take a quick look at auto rotation, just very brief look, I mean what exactly it means, and it is not very relevant for direct drive multicopters, but if you have rotary wing, like pure rotary wing helicopter kind of things, then there is a some advantage, because it provides you with some kind of fail safe mode of operation. Okay. Okay, so we stop here now.